All right, welcome back. We just had that really long video talking about all these different isomers and ways of rearranging things and also electron configurations. What are we going to talk about next? We're going to talk about the spectrochemical series. What's really cool about the spectrochemical series is what we have down here in the bottom is a picture of a bunch of different solutions. Like, wow, look at all those pretty colors. But what I'm going to tell you is that every single one of those solutions, the color in that solution comes from the cobalt 3+ ion. So the yellow solution, the color is coming from cobalt 3+. The green solution, the color is coming from cobalt 3+. The purple solution, the color is coming from cobalt 3+. So how can it be that cobalt 3+ is producing all of these different colors? That seems very, very odd, right? Well, the first thing we have to remember is, what do these colors mean? Right? When we see a yellow solution or a green solution, what does it mean is going on? And that brings us back to our favorite friend, the color wheel. Roy G. Biv, if you've heard that before. Red, orange, yellow, green, blue, and purple or violet. And what does it mean? It says, well, if we are seeing, let's say, a yellow solution here, that means that solution is letting through yellow light. Right? There's light hitting it, and it's letting through the yellow light, which is why our eye can see it, because our eye is being hit by yellow light. So we call it a yellow solution, but it's actually a solution that is not doing anything to yellow. What's it doing? Well, it turns out that primarily the thing it's going to be doing is absorbing the color that's opposite the yellow on my color wheel. So primarily this yellow one is absorbing violet. Now, that's not the only thing it's doing. It's absorbing other colors in different proportions too, and that's how we get so many different colors out there, right? There's not just 6 colors in the world. But the primary thing it's going to be doing is absorbing somewhere in the violet. Whereas this green solution here, by the fact that it's green, means the green is hitting my eye, which means the solution's not absorbing any green. It's letting all the green through. What's it primarily doing? For a green solution, it's primarily absorbing the thing across from green, which is the red. So my green solution here is primarily absorbing red. Now, so we're saying these things are absorbing. That's really nice, but how do things absorb light? What is actually going on a fundamental chemical level for something to absorb light? And you may or may not have covered this before. Hopefully you have, but if you haven't, I'm going to tell you something really, really cool. What happens when most things absorb light is electrons move from one level up to another level. And this energy here, right, we know that electron energy levels are quantized. So this is a very, very specific energy, right? I'm just going to make up some energy, right? This is the energy of 394 nanometer light. Whatever it is, 394 nanometer light will hit that and make that electron be able to fly up to that next level. That's what's happening when something absorbs light. But if you hit this guy with 380 nanometer light, it's just going to go through. It's just going to pass through, because that one only absorbs 394 nanometer light, because it's a very specific energy. Now, there's some fuzziness to it. We're not going to get into right there, because things are packed together and it kind of makes those, yeah, we won't get to that. Anyway, so the 380 just kind of goes through. So we're going to see this solution primarily absorb 394 nanometer light, but 380 nanometer light is mostly going to go through. So that's what's happening here. When we say this green solution is primarily absorbing red, that means somewhere in there, there are 2 energy levels that are spaced by the energy of red light. But in this one, in the yellow one that's absorbing violet, there are some in there that are spaced by the energy of violet light. And that's what happens when we absorb all that different light. Now, what happens when electrons jump up is they also can fall back down. So yes, we brought this electron up, but it can also fall back down. And some things do that in one step. It releases the exact same amount of light and energy that we put it into it, but that's actually not very common. What's much more common is for this guy, when he's coming down, to take a different path and go to another level, and then go to another level, and then go down here, and eventually relax back down to what we call the ground state, or the lowest energy state. But each one of these is going to be lower energy. And the lower energy, what's the next lowest energy light from visible light? It's infrared. And how do we experience infrared light? We experience infrared light as heat. So what happens when you go out and you're wearing black clothing? Black clothing is essentially absorbing all the different colors of light. You get really hot if you're in the sun in black clothing. Why? Because it's absorbing all that light, and as it's falling back down in these kind of lower steps going, it's releasing a bunch of infrared energy, and it's heating you up. Whereas if you're wearing white clothing, it's essentially absorbing no colors of light. It's reflecting all the light that's coming onto it. And so there's not much of that transitioning back down and giving off heat, and so you don't get as hot in white clothing. It all comes down to the movement of electrons. Whether you get hot in your clothing or not in the sunshine comes down to the movement of electrons. I think it's really cool. But anyway, so that's what we're going to be talking about here, is how can we change, right? I told you that it's cobalt ions in every single one of these solutions that's responsible for the light. So what has to be happening is something's happening in the solution that sometimes there's a big spacing in the energy levels of cobalt, and sometimes there's a small spacing in the energy levels of cobalt. But our thoughts about that are like, no, that's not how it happens. Cobalt has fixed energy spacings, and so cobalt's always going to be the same color. And that would be true if we were just talking about cobalt all by itself. But we're not talking about cobalt by itself. We're talking about cobalt in the presence of cyanide, or in the presence of nitrite, or in the presence of ammonia, or in the presence of oxalate. And those things are going to change how the cobalt's energy levels are spaced, right? How you act and how you behave and how your energy levels are depends on the people you're hanging around with, right? And the same thing with these metal centers. Who they're hanging around with is going to change how they behave. And the theory that we're going to use behind all of this is what's called crystal field theory. And if you look at this picture at first, you're like, whoa, that looks like a lot of information, way too much going on. But it's not that bad. It's not that bad. What crystal field theory says is this. Da-da-ding. We start with the d orbitals on our cobalt. 5 d orbitals, all energetically equivalent, right? All those, if you remember all those funny ones, the dx squared minus y squared, the dz squared, the dyz, the dxz, and the dxy, and you're like, I'm dizzy, Professor Clemens, can you stop that? All right, those are all roughly energetically equivalent. But a funny thing happens when you start to bring in ligands bonding to that metal center. What happens is, if you see this set of coordinate axes are x, y, and z. I'm not going to go into the reasons here because that's an entire course in group theory, and that's pretty intense stuff, so we're not going to cover it. But I'm just going to tell you, when things bond to these metal centers, they're always going to bond along these sets of axes. So it's going to bond along the z-axis, it's going to bond along the y-axis, and it's going to bond along the x-axis. So as I start to bring these things in, and let's say I'm bringing in water, it looks like this, and it's got my negative here, right? We've got these d orbitals. Now we know there's some electron density in these d orbitals, right? We haven't completely taken all the electron density out of them. Cobalt's got a bunch of d electrons left, even in its +3 state. And so there's some electron density there. Then I bring in this thing that's negatively charged. And as I go along this z-axis, say, right, as I bring this negatively charged or slightly negatively charged oxygen in, it's going to interact with the electrons that are already present in these orbitals here, and it's going to raise their energy ever so slightly, right? You've got electrons approaching electrons, and so there is going to be an increase in the energy level of these orbitals because there's now something kind of pushing against it. Now, there's this bond that's created between the metal and the ligand, and that totally counteracts the energy of it, so we're overall going to be really, really good. But you can see that for my dxy, that was the one I was just showing you here, dxy, it's going to increase the energy level of that just a little bit because I'm getting closer to it, but I'm not exactly interacting with them directly. And it turns out the same thing happens if I came along the z-axis here. When I have the dyz, I've got electron density in these orbitals here, and I'm bringing in a little bit of electron density in my ligand, but they're not interacting directly, right? There's the orbital is not right on that z-axis. It's a little bit off that z-axis. And it turns out that the amount of interaction you get, the amount of increase in energy to these orbitals is roughly the same in the dxy as the dyz, and also in the dxz. So these ones that are not exactly on the axes. You don't have to remember the xy, the yz, the xz. I don't need you to remember any of that stuff. But I want you to understand that there's these kind of three orbitals where the orbitals exist not on the axes where things are bonding, and that's going to increase my energies just a little bit by kind of essentially electron repulsion, right? Now, if we bring things in along the z-axis to my z squared or my x squared minus y squared, what's going to happen? If I bring things along my z-axis here, and I've got some electron density in this orbital here, and I bring in something that's got some electron density, those electrons are going to be right on top of each other. They're going to be kind of pushing against each other. And what's going to happen to the energy of this guy is it's going to be raised up by more because of that repulsion. And so my z squared orbital goes up by quite a lot. The same thing happens here. If I bring in something along these axes here, not so much on the z, but I'm not going to do much along the z-axis. If I bring so much on the x or y-axis, it's going to raise the energy of my x squared minus y squared d orbital by quite a lot, and I get this one up here. So what do I get? I get that 3 orbitals increased by a little bit of energy, 2 orbitals increased by a lot of energy, and all of a sudden these 5 d orbitals that used to be energetically equivalent, we call them degenerate, are now different. And we've got 3 that are at a low energy, 2 that are a high energy, and now there's this difference of energy between them, which we just call delta. Not delta anything, just delta. Okay? Again, so many different letters in the alphabet, so many different Greek letters. They could have used any other thing. They chose delta, right? You know, they might as well have chosen K, because that would just been great just to throw another K at us, right? We're usually used to saying delta T, delta S, delta G. This is just delta all by itself. And that is what we call the d-level splitting, or the d-orbital splitting, right? It's the energy difference between the ones that only raised a little bit and the energy of the ones that raised quite a lot. What does this matter? What? Okay, so yes, okay, fine. There's these things depending on how they interact, and so you get this splitting. Well, what do we say? All color comes from electrons traveling from one orbital up to another orbital. So if I've got electrons in my yz orbital, and then I shine some light of just the right energy, I can get that electron to go up to the x squared minus y squared orbital, or the z squared orbital, but only at the energy of the light exactly equal to delta. All right, so I've got cobalt here. I've now split the orbitals, and so I've got this delta for cobalt, and I should really still only get one color of cobalt, shouldn't I? Well, it turns out that because we're talking about the electron density being something that really helps with this repulsion theory, things with different electron densities and different ability to donate electrons and stuff are going to affect these things differently. It's going to affect it differently if I bring in this giant iodine with this kind of like massive cloud of electrons versus if I bring in something like water, which is a little more concentrated. That charge is over on the oxygen side. I'm going to be splitting these things a little bit different. So it turns out this delta varies with the ligand. And there's some ligands that cause a very large delta, and there's some ligands that cause a very small delta. And as that delta changes, the light color that's absorbed by the cobalt also changes. Because I'm still, for example, taking it from the yz orbital up to the x squared minus y squared orbital, but if that delta changes, I'm absorbing red light in a case where that delta is small. I'm absorbing purple light in the case where that delta is big. And my solution is going to have a different resultant color that I could figure out by using a color wheel if I wanted to. And so that's how this spectrochemical series works. All of these different solutions, all that color comes from cobalt, but it comes from different energy spacings, all in cobalt, as a result of the identity of the ligands we're bringing in. And that is crystal field theory. It's really, really neat. It's actually a relatively simple explanation for a fairly complicated phenomenon. So what are we going to do with this? Well, there's a few things we're going to do. We're going to do some language here. Delta is large and delta is small. So if we've got a large delta, we've got these 3 D's down here. There's a huge gap to go up to the next one. If we've got a small delta, there's a relatively small gap to go on to the first one. So what we're going to do is we're going to start doing our Hund's rules. We go across the periodic table, and we're going to start filling electrons. 1, 2, 3, 4, 5, 6. You remember we unpair before we pair. 1, 2, 3, 4, 5, 6. So I've got something with 6 d electrons at this point. And there's not much difference between them, except, right, when this delta that is small, oops, I did this wrong. I actually wanted to start with 3. I'm like thinking to myself, that's not going to work. So I'm going to start with 3. 1, 2, 3, 1, 2, 3. There we go. So I've got 3 d electrons in there. And that just comes from the state of our ion. If our ion has a configuration of 3d3, then I'll have 3 electrons. If our ion has a configuration of 3d7, then I'll have 7 electrons. So that's why finding those electron configurations of the ions by taking out the 4s first, that's an important thing to be able to do. All right, so I've got this thing that's a 3d3, and there we go. There's not much difference between when delta is large and delta is small. But what happens is what happens if we want to put in a 4th electron. If we want to put in a 4th electron, I always have choices. I can pair that electron, or I can put that electron into a different orbital. When delta is large, if I wanted to put this up here, that electron would need a lot of energy. It wouldn't really be happy up there. It would be much easier to put it down here. And although there is a cost with pairing electrons, it's relatively small compared to trying to put that electron way up at this higher energy level. And so I'm going to pair that electron preferentially. But in the same case, if I'm adding a 4th electron, when delta is small, when that change is very, very small, it turns out that it's actually going to be more energetically favorable just to put that up to the next level than it is to pay the penalty of having to pair that electron. And so now I start to see a difference of how the electrons are actually configured when delta is large and delta is small. When delta is large, I tend to pair before going up. But when delta is small, I tend to go up before pairing. And there's consequences of this. When delta is large, I tend to pair these electrons, and I tend to have less unpaired electrons. It's not always true, because if you don't have enough electrons to start pairing them, it doesn't matter. And this one tends to have more unpaired electrons. And so we actually have some terminology for this. When we have less unpaired electrons, we're going to call this a low spin complex. When we have lots of unpaired electrons, we're going to call this a high spin complex. Why spin? Why are we talking about spin here? You remember electrons have a spin. They rotate one way or they rotate another, and they tend to align their spins. And so when you've got these electrons in there and they're all kind of aligned the same way, the spin of that molecule and how it interacts with other things, electromagnetic fields and other things, is going to be different, right, a magnet, than in a case where you've got this low spin complex. All right, so when delta is large, we tend to get low spin complexes. When delta is small, we tend to get high spin complexes. Now, this is true. This language works even if I only had 3 electrons. So I'm going to erase my last electron here. Even if I only had 3 electrons, when delta is large, I still call it a low spin complex, even though it's got 3 unpaired electrons. And when delta is small, I call it a high spin complex, even though it also has 3 unpaired electrons. There's no difference between the number of unpaired electrons in each one of those scenarios. It's just a language that's actually related to delta, not whether you actually have a lot of paired or unpaired electrons. So it's a bit confusing, but just be aware of that. Now, how do you get a low spin complex? How do you get a high spin complex? Well, in order for delta to be large, there's got to be a lot of interaction between your ligand and those orbitals, those d orbitals, to get that splitting to be large. And we call that excuse me, a strong field complex. right? There's a strong field interacting between your ligand and your orbitals to cause delta to be large. Here, we call this a weak field. So they're kind of synonyms, even though they kind of say the opposite thing, right? A low spin complex is a strong field complex. A high spin complex is a weak field complex, okay? And again, that doesn't actually depend on how many paired electrons or unpaired electrons there are. It actually just depends on how big that splitting is. And I'll show you where the cutoff is in just a moment. Right. One other thing. Let's say I had 6 electrons. Oops. Helps if I do this correctly. Right. In the case of the large splitting, I'm going to go down here and I'm going to make those 6 electrons go into my lower orbital. Right? Because it's so much energy going to that next orbital, I'm not going to do it. But in the case of the small splitting, I'm going to stick the 4th and the 5th one up there, and I'm only going to pair that 6th one down at my lower energy. And so here I've got 4 unpaired electrons, and here I've got 0 unpaired. Okay? And if you remember, there's some language associated with having unpaired electrons versus not unpaired electrons. When I have 0 unpaired electrons, we call that diamagnetic. Ooh. And when we have 1 or more unpaired electrons, we call it paramagnetic. Paramagnetic molecules will respond to magnetic fields. Diamagnetic molecules will not respond to magnetic fields. All right, lots and lots of language to keep track of here. So you want to write those down somewhere, kind of organize them to make sure you understand what we're talking about. The low spin and strong field literally just says how big is delta. Doesn't matter whether there's unpaired electrons or no unpaired electrons. It just says that as we add these electrons, low spin means we're going to pair them preferentially before we go up to the next level. Whereas in a high spin complex, we're going to leave them unpaired preferentially because delta is small, whether we have 1 electron in there or 7 electrons in there. Okay. Diamagnetic means that when we finish our configurations, we have no unpaired electrons. The only way to have that is either to have 0 d electrons, 6 d electrons, or 10 d electrons. That's the only way you're going to get diamagnetic. Mostly you're going to get paramagnetic when you have at least 1 unpaired electron. 1, 2, 3, 4, 5, doesn't matter how many you have. 5's the max of unpaired electrons. All right, so lots of language. The next thing we have to figure out is how do we know whether we're going to have a high spin or a low spin complex, how we're going to have a strong field or a weak field. And it turns out people have just studied this quite a lot and said, hey, here's what we're going to do. How do we tell it's a high spin or a low spin complex? I had a note page there and it's gone now. All right, how do we tell if it's a high spin or a low spin complex? Is you're going to use something called the spectrochemical series. Now, I mentioned that in that first slide of this chapter, or of this section, where I said show these different solutions. We called it the spectrochemical series. And what the spectrochemical series is that a ranking of the strength of the field of different common ligands. So cyanide is the strongest one. If you're pairing cyanide with your complex, you're going to get this very large d-orbital splitting, and you have a low spin complex. And cyanide is more powerful than the nitrite ion, which is more powerful than ethylene diamine, than ammonia, than water, than OH minus, than F minus, than chloride, than bromide, than iodide. Okay, so you don't have to memorize that. Don't memorize it all, but be able to use it, right? Given the spectrochemical series, you should be able to tell which is going to have a larger splitting. If I take cobalt and I pair it with cyanide, and I take cobalt and I pair it with ammonia, you should be able to tell me the delta is going to be larger in the cyanide complex than it is in the ammonia complex. Or fluoride versus ethylene diamine, you should be able to say, oh, the ethylene diamine is going to have a larger delta than a fluoride complex. Now, what's interesting about this one is people will usually draw a line here after the 4th one, bing, 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 bing. And we're going to call these one the strong field, and we're going to call these ones the weak field. Right? Big delta, little delta. Right? So if you're making a complex and you're making it with water, right, that's what we call a weak field ligand. And chances are what's going to happen there is you're going to have a very small delta, and things are going to preferentially unpair. So you're going to fill the 3 on the bottom. The next one's going to go up to that upper level because that delta is very small. Whereas if you're using one of the strong field ligands, that delta is much larger than the energy cost of pairing. And so when you fill in those first 3, ding, 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 the fourth one is going to pair versus going way up to that large delta there. So that's generally how people consider this. Another thing we can do is we can look at the actual energies of these things. Let's say we had a complex and it was, let's say, like I said, I had some ones here. Let's say it was a yellow complex. So we had a solution that was yellow. What we can actually do is we can estimate the d-orbital splitting in a yellow solution. So we're going to estimate delta, the d-orbital splitting in a yellow solution. How are we going to do that? Well, turns out we're going to go back to some of your first semester general chemistry knowledge, and see if you remember this. E equals h nu. The energy of light is equal to Planck's constant h times the frequency of the light, or E equals hc over lambda. Energy is equal to Planck's constant times the speed of light divided by the wavelength. And we're going to use that to calculate the energy of light for a given wavelength of absorbed light. Right? And that's really important because when we see a solution that's yellow, we have to remember that the yellow is what's actually seeing our eye or hitting our eye, so it's not what's absorbed. What's absorbed is the opposite one. And so a yellow solution is actually absorbing purple light. Now, purple light, you can see from this color wheel, goes from about 430 or 400 to about 430 nanometers. So we're going to estimate that somewhere in the middle. We're going to call it 415 nanometers. So we're going to say the wavelength of absorbed light in a yellow solution is that of purple light, because purple light's being absorbed, yellow is transmitting, and so we're absorbing purple light. So it must mean that somewhere in my complex, there is some d-orbital splitting that is exactly equal to my purple light, and we're estimating, right, of about 415 nanometers. That's going to be my delta. But I have to turn that delta into an energy by using my equation E equals hc over lambda. So I say E equals h. If you remember what h is, it is, let's see, I wrote this down. Yeah, 6.626176. One of those numbers I memorized since high school. I have no idea why. 6.626 times 10 to the minus 34th. And we'll get to the units of that in just a second, times the speed of light, 2.997925 times 10 to the 8th, but we're going to go ahead and round that, 3.00 times 10 to the 8th meters per second. And then lambda. We can't just put 415 nanometers down here because those meters wouldn't cancel. And so we need to convert that into meters. Remember, nano is just 10 to the minus 9th, and so we can actually just write 415 times 10 to the minus 9th. And that's not proper scientific notation, but your calculator doesn't care. You can type that into your calculator all day long, and it'll calculate it just fine for you. All right, if you remember the units of Planck's constant, and remember, I always love units, are joule seconds. How do I know that? Because my meters are going to cancel. I need something to cancel seconds because I want to get joules over here as my units. All right, so we plug that into a calculator. Again, I actually had a example here, but the paper went away. And now what I can't find is my actual calculator either. And so that's going to make calculating this very, very difficult. I had a calculator here just the other day. Look, I found it. All right, so I'm going to take my 6.626 times 10 to the minus 34th. I'm going to multiply by 3.00 times 10 to the 8th, and I'm going to divide by 415 times 10 to the minus 9th. Make sure you're using the built-in scientific notation on your calculator. If you're typing 415 times 10 to the minus 9th, you're going to get way off answers. Okay? You should always get answers that are roughly 10 to the minus 19th in order. Okay, so I get 4.78987 blah, 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 times 10 to the minus 19th joules. That's a very small number. 10 to the minus 19th anything is a very, very small number. Why is that number so small? Because that's per photon. If you remember, light comes in photons. That's for a single thing of light coming in. Boom, it's got 10 to the minus 19th joules. We don't really want joules per photon. We generally talk about things in joules or kilojoules per mole. So what I'm going to do is I'm going to multiply that by Avogadro's number, 6.02 times 10 to the 23rd photons per mole of photons. And when I do that, 6.02 times 10 to the 23rd, I get 288,351 joules per mole. I'm going to convert that into kilojoules per mole by saying 1 kilojoule per 1,000 joules, and I get 288.4 kilojoules per mole. I can probably round that to my nearest whole number, 288 kilojoules per mole, since I'm just estimating anyway. Right? And that is the energy level splitting of a solution that's yellow. That's really, really cool. I mean, we're talking about like saying, hey, this is orange, and being able to figure out that somewhere in there, there's 2 electron energy levels that are spaced by 200, or I should say yellow, 288 kilojoules per mole. That's crazy to me that a simple, just basic observation of color can tell us electron energy level spacings. I love it. I think this stuff's really, really neat. Okay? So you're going to get a chance to do that yourself and to figure out what some different things are. So you should be able to do this kind of calculation where say, hey, take a orange solution and figure out what the d-orbital splitting is. Or I could give you a d-orbital splitting. You could do this calculation backwards to find a wavelength, and you could tell me what color it is. Remember, the wavelength that you calculate is not the wavelength of the color that it is. It's the wavelength that's absorbing. So if you did this calculation backwards, I gave you an energy, and you found out that it was 595 nanometers. You'd be like, okay, that's in the orange right here, and you would not say the solution is orange, because what the solution is doing is absorbing orange, and you'd say, hey, look, I must have a blue solution, because that's what it's not absorbing. So you always have to remember that step of color is not the same thing as absorbing. Right? So there's always that additional step of color versus what it's absorbing. All right, be able to use the spectrochemical series, understand which are the strong field, those first 4, which are the weak field, those next ones, and use color to calculate different deltas. All right, so here's one. The vanadium 3+ ion is a beautiful green color in solution. If you've ever worked with vanadium, the colors it produces are some of the most beautiful, pure colors you've ever seen in your life. So here's a green one. This picture doesn't do it justice. But it's got 6 water molecules. Is it a high spin complex or a low spin complex? And again, you don't need to know much about vanadium to do this one. You just need to worry about the parts that matter. All right, go. What'd you come up with? Well, hopefully you ran up to your spectrochemical series and be like, hey, water is a weak field ligand. A weak field ligand means my delta is tiny, and I'm going to preferentially start to fill electrons up here before I pair them. And that means if I've got a bunch of electrons, I'm going to have lots of unpaired electrons. But remember, it doesn't matter how many you have. The language is that this weak field complexes are going to produce high spin, right, unpaired electrons. All right, we've got the same thing, but now we've got a vanadium 4+ ion, beautiful blue color in solutions. We've got this guy here. Beautiful blue color in solution, complexes with 5 water molecules to form this vanadium oxide water complex. What is the approximate d-orbital splitting delta in the units of kilojoules per mole? Now remember, in this one, you're just making some estimates. Your estimates might be slightly off from mine, and that's okay. You want to find one that's a little reasonable. If you might have to do more than one calculation to figure that out, you might have to do that. But there is one of these that's reasonable and others that are not so reasonable. All right, go. You're still going. It's a movie. You can stop now. Oh, okay. Anyway, so what did you come up with? Hopefully you ran to, let's see, I've got beautiful blue color. Ba-ding, that means it's absorbing orange. let's pick somewhere around, I just want to make sure I'm picking the same number as I did. Let's pick somewhere around 620 nanometers, somewhere in the middle. Again, you might have picked a slightly different number, and that's okay. Anything in that range of 580 to 650 on a test would be good. Don't pick 580, don't pick 650. Best to pick somewhere roughly in the middle. But, you know, I'm not that picky about it. If you picked 560, it would have been, hey, no, wrong color. Okay? So E equals HC over lambda is 6.626 times 10 to the minus 34th joules seconds times 3.00 times 10 to the 8th meters per second divided by 620 times 10 to the minus 9th meters. If you do that, you get 3.2 times 10 to the minus 19th joules for photon. And if you multiply that out by Avogadro's number, you get 1.93 times 10 to the 5th joules per mole, or 193 kilojoules per mole. And so you get the answer of, dun, 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 A, that first one there. All right, so that's what I expect you to be able to do, is that calculation forward or that calculation backwards, remembering the step of color is not the same thing as absorbing. Just a couple things to end the chapter with. Where do we see these complexes in biology? Cytochrome C. What's in the middle of cytochrome C? Cytochrome C, metal center, bonded in a planar configuration to 4 other things. The heme center, right? Our blood. What is there? You've got that iron center coordinated to several different things. Why only 4 different things? Because it turns out you're going to coordinate to oxygen on the top and the bottom, which is the transport of oxygen. Okay? So there's the hemoglobin. It's actually got 4 different heme centers, and you can see it a little bit closer here with the iron attached to the nitrogen and all sorts of other things supporting it, but still room on the top and the bottom to grab some oxygens. Carbonic anhydrase, if you like to breathe and not die, okay, this is a great one to have. It allows the conversion between water and carbon dioxide, H plus and bicarbonate ion, which is kind of our buffer maintaining system in there. How does it work? It's a catalyst, it's an enzyme, and it speeds that reaction up in any way that we want it to. But how does it work? Oh, look, there's a metal center down in there coordinated, and that metal center is what does a good chunk of the work. The rest of the stuff around there is scaffolding to help the coordination and bringing things in just the right way to take this reaction from something that's relatively slow to something that's amazingly fast on demand. So cool, all the different things that we see in nature. All right, that is it for the transition metals chapter. We had a couple videos on it. We talked about identifying all the different isomers, trying to write electron configurations using the spectrochemical series, understanding the language with regards to spectrochemical series, and then calculating deltas based on solution color or wavelengths, or vice versa, are the things I expect you to do. All right, thanks so much for listening. Have a wonderful day.